And
so it's recording right now.
okay. So
Okay. Hello, everyone. My name is Aayush, and today I'll be discussing on how batch normalization helps in optimization. It's a bit lagged. So here, basic contents, we'll go through the introduction of batch norm, various properties, and what it addresses in the original paper, the internal covariate shift. Then we'll go through the methods and results from this current paper and some discussions on them. So in deep learning, we generally require a large variation in data for training, and this large variation causes a lot of change in the input distribution, not only the first layer's input distribution, but also intermediate layers distribution changes rapidly. This makes the underlying problem harder to solve. It needs a lower learning rate and gradient predictability decreases, as well as the network takes a slightly longer time to converge. So to tackle these issues, building on concepts from the 90s, batch norm was introduced, the formally with this formulation. And this is a batch norm version of a network training where they show the same network with and without different types of batch norm and how quickly it converges. So if we see the dark blue line here, it's a network with batch norm and the learning rate increased by 30 times the original network, and we see in very few steps it converges to the same accuracy as the original one. Similar with a different type of network in different settings. The red one here shows the network without batch norm. It's the standard network, and applying batch norm to each layer significantly increases the training accuracy, as well as similar case in test accuracy. One thing to notice here is the learning rate affects outcome of batch norm a lot. So networks with very low learning rate show similar performance with and without batch norm. So one of the key findings from earlier batch normalization papers were that it improves the stability during training. So we see the blue and orange lines here. These are the mean and standard deviation across all the layers of a 110 layer ResNet model. And we see that it's fairly predictable and within a certain range, whereas the mean and standard deviation across layers on a non-batch normalized network varies a lot from initial layer to the final layer. So in terms of in mathematical way, batch normalization is normalizing the input values using mean and standard deviation across each mini batch. So we get our set of input values and we pass them through certain weights. Then we get the mean and variance for this set of mini batch, and we also learn a scale term and a shift term. So this scale and shift parameter, what they basically do is you first normalize the values using the mean and variance, then the normalized values are scaled and shifted so that each layer can learn a different scale and shift parameters. So first, in the algorithm, first they learn the mean for each mini batch, get the variance, normalize it, and scale and shift. This is the full batch normalization layer. And the advantages of using batch norm in studied through various papers is that it scales the distribution of the input features, so they are all normalized, and it also limits the internal covariate shift, so which is one of the key motivation behind the original paper. The other advantageous property of batch norm notice was it prevents exploding and vanishing gradients because it has more predictability in the gradients. And batch norm generally shows that the network has faster convergence because of a stable gradient descent, and we can apply higher learning rates. So we'll go through all of these properties and see which one affects the network more. And one of the parallel drawn was batch norm is also acting as a regularization term, where we have a mean subtraction and standard deviation division. This is additive noise and multiplicative noise. So for each mini batch, it has some noise associated with it. So we can then look at the internal covariate shift, which is why the paper from 2015 introduced batch norm as. Here they define the covariate shift as the change in input distribution. So due to the previous layer's parameter update, the values for the next layer would be shifted quite radically. And this is very detrimental in deep neural networks as the propagation is hierarchical. So if something fails in a very early layer, then it's propagated throughout the network. And the covariate shift also creates a shift in the underlying optimization problem. So it's harder for the network to optimize to a certain minima when the values for each mini batch changes drastically. So the main idea was if they control this shift in the input parameters for each layer, so if it's not changing rapidly a lot, then the network would be able to converge faster. So the first thing this paper from today measures is the relation between stability of covariate shift and the effect in batch norm. So what they do is they artificially inject some noise after the output of each batch norm layer. So if this is a regular batch norm implementation, then after the output of each batch norm, they put some non-zero mean and non-invariance random noise. And this noise is it's like manually increasing the covariate shift in each layer. So this brings out severe data perturbation where each batch norm output in each sample has a random shift due to the noise. And then they measure the effect of this instability on batch norm. So they check if this artificially induced noise, which in theory increases the covariate shift, would make the network learn any slower or if it affects the convergence. But what they notice is if we see the graph, this blue and magenta are networks with standard batch norm and noisy batch norm. So even though a lot of noise was actually added and the covariate shift was increased in the training phase, the accuracy of network with noisy batch norm is very similar to the pattern is similar to the one with just normal batch norm. So they don't notice any significant performance difference between these two variants. When they measure the activations for certain layers, they see that there is indeed a lot of covariate shift. So the data distribution is noisy, it is not centered as we go in deeper layers, like in this third column. So the covariate shift has indeed increased. However, even with that, the test accuracy and training accuracy for batch norm, normal batch norm, and noisy batch norm remains similar. So it shows that the original claim that batch norm is like it makes the covariance shift more stable doesn't hold in this test. So even in this, in all of these graphs, the magenta is the network with batch norm with noise added, and you see like the difference in variance is very unstable in that, and difference in mean is also very unstable for each of these layers. So it shows increase in the covariance shift, but no effect in the test and training accuracy. So now they measure if applying batch norm affects, like reduces the shift itself. So this is to check the effect of cross-layer dependency. So if we apply batch norm throughout the entire network, then it essentially should reduce this shift. And if each layer has reduced covariance shift, then a lot of change in one layer should not affect a lot in the further like future layers. So to measure this, they take the difference between the gradients before and after applying batch norm. So for a given layer I, they calculate so this G E of I is the gradient value before applying update at time t for layer I, and G prime is the value of gradient after applying the update. So the update is applied to all the layers previous to layer I, but the subsequent layers are kept the same. So if batch norm reduces the internal covariance shift, then once we apply a new update, the next set of values should be very similar to the set of values from the previous layer. So the difference between these two terms should be very minimum. But it seemed like when they did the experiment, they found that whether they apply batch norm or whether they train the network without batch norm, the change in gradients are almost similar. So they report similar pattern. So here the red one is layer with network with standard batch norm, blue is the standard, sorry, red is the standard network, blue is the network with batch norm. And the L2 difference between G and G prime, which measures the difference between two subsequent steps, is almost identical. And the second column is cosine angle, which is also similar. This was for a VGG network, and in some network, in certain cases, they noticed that using batch norm actually increases this gap. So in this network, in the DLN deep linear network, the L2 difference actually increased after applying batch norm. So it's contrary to the original belief that batch norm would reduce the shift. Here it instead increases the shift by a lot, like it's significantly increased. However, the performance of the network is better when using batch norm, and the learning rate can be higher when using batch norm, and it also converges faster. So through these set of experiments, this paper shows that the original belief of batch norm just solely depending on the covariance shift, and that batch norm reduces covariance shift is somewhat disproven. So this is just showing the batch norm model performing better, has higher accuracy, lower loss, even with increased covariance shift. So then we look at different other effects of batch norm. So maybe internal covariance shift is not the only factor might be one of the factors affecting network training due to batch normalization. So the other effects, some of the other effect would be how batch norm is a smoothing of the loss landscape. So batch norm does reparameterization, and it's like this reparameterization smoothens the landscape of the loss parameter. So the scale and shift that's applied in batch norm in each layer causes the underlying optimization function to become smoother. And it also should be minimized. So it also finds the optimum Lipschitz constant, which will come to later. So in my understanding, the lower Lipschitz constant would imply the function has a lower bound, and having a lower bound would improve the optimization for a given function. So they observe that when they apply batch norm, this constant is usually lower or equal to the network without batch norm. And finally, batch norm's reparameterization also increases the gradient's predictability. So with a predictable gradient, you can apply a step with a higher rate, and that means we can use a higher learning rate for training. And the beta smoothness is another property. This is the difference between the highest and lowest gradient change for each step. So if the ratio is smaller, it means you have a more predictable gradient direction, and the loss landscape is smoother compared to the problem without batch norm. So the rate of change for loss is also smaller, and it has smaller magnitudes. And finally, it's shown that it improves the ellipticness of the gradient. So this basically correlates to a tighter bounded function, and it improves the optimization. So to measure the optimization landscape, so in each training iteration, we have, if we are at a point x of t and apply this update, we reach another point. So they take a step in the network training, define gradient direction, and use different step sizes in the same direction. So they check what the loss is when you apply different step size, but keep the direction constant. One of the measure they use is the variation of loss. This gives the idea about the loss landscape, and they measure the gradient in each step with different rates, being eta between 0.05 and 0.4. The other is they measure the variation of this gradient itself. So they check how much the magnitude of the gradient itself changes and how it is different with and without batch norm. So in this, we look at variation of loss in the standard network. First column, you take two different iterations, one trained for 100 steps and another for 15,000 steps. Then in both VGG and DLN, it seems that without batch normalization, if you are using a higher rate, so the step size is high, then in a small subspace window, you have a very large gradient change. Whereas with batch normalization, even if you have a very high rate per step in the same subspace, the rate of change is very low. This kind of shows that if we have a very low learning rate, and if you have enough data to train on and enough time, then you can train the network without using a batch normalization layer. it would eventually converge to the same place. But with batch norm, you have this extra ability to use higher learning rates. And the higher learning rate also implies that the loss landscape that you're looking at, so even if you have a gradient direction and you take a large step in that direction, the chances of you getting exploding a vanishing gradient suddenly is very low there. Now we look at effect between batch norm and the Hessian. So this is a study from another paper where they see that when batch normalization is applied, then the largest eigenvalue of the Hessian matrix is smoother. So it's like there's less outlier in the eigenvalues, and having less outlier means the optimization is faster. Without batch normalization, these observe more outliers in the eigenvalues, and it slows down the optimization problem. So here they show the eigenvalue ratio, so the ratio between the largest and the smallest eigenvalue for each Hessian matrix at different training steps, and blue is the blue one is the network with batch normalization. It's constantly stable ratio, so it has similar ratio between different eigenvalues in the same Hessian matrix. This is one of the theorem from this paper where they prove that the gradient update with batch norm is always less than or equal to the gradient update without batch norm. And in my understanding, this would be a Lipschitz constant here, which based on the Lipschitz property is defined as the bounding constant. So we will always have a solution within this bound. And this relation, which they prove in this paper, shows that batch norm underlying bound is less than or always equal to the network without batch norm. Similar for smoothness of the network, if we have the, if we look at the Hessian matrix, and it's a similar representation where this scaling term is used as the Lipschitz constant, and the network with batch norm has lower bound than the network without batch norm. So it's faster. In conclusion, we find various underlying effects of batch norm, that the reparameterization due to scale and shift eventually affects the optimization and smoothens the loss. It also makes the gradients more predictable and maximizes Lipschitzness of the function, which in turn allows a higher learning rate and also controls the gradient shift problem, resulting in a faster optimization. Here are some references I used for this presentation. That's all. You want to stop recording?
No, you don't stop it.